In this video, we are going to relate the gravitational waves whose propagation we just studied to the sources that produce them. This relation is provided by the equation that we derived in the weak field approximation, which has this form at the lowest order. And let me remind you what are all these things. So this is the wave operator, as you know. Chi is related to the coupling constant in this way, so the Newton constant. In this way we are work in units of C equal 1. H bar mu nu is this combination of the tensor H mu nu, which is the perturbation around Minkowski of the. Okay, so we can write the metric, the complete metric, as Minkowski metric plus this perturbation times chi. Okay, finally, this T mu nu rho is the Rosenfeld energy momentum tensor. It is the special relativistic energy momentum tensor that you obtain if you start with the gravitational energy momentum tensor and replace the metric by the Minkowski metric. Then it satisfies this condition. Okay, the divergence, this simple divergence in flat space-time vanishes. Okay, well, we want to solve this equation. Okay, we will see under which conditions and for which kind of T mu nu's, but in general we want to solve this equation, which is an inhomogeneous wave equation. And the way to do it, as you know, is to find the Green's function for the wave equation. So the Green's function is defined as the function that satisfies this equation, in which the source, which here is this, is replaced by a delta function. You note that if you find a Green function that satisfies this property, then automatically H mu nu will be given by chi, and then the integral, the H mu nu evaluated at x will be given by the integral over T for y, g x minus y, and then T mu nu evaluated of y. Okay, so the first thing that we have to do is to find this Green's function. This Green's function is a linear combination of two solutions of the equation. The most general Green function is a linear combination. And these two main solutions are the so-called advanced and retarded Green's function. One of them propagates signals to the future and the other one to the past. So it is the retarded Green's function, the one that propagates signals to the future, that the one that we are going to use. Okay, it will, when something happens in the matter distribution, okay, the signal will be propagated by the Green's function, and H mu nu will change at a later time. We will feel this change at a later time. So that's why we should use this retarded Green's function, and the retarded Green's function is given by this expression. Okay, and with 4 pi here. Well, if you want to see how this Green's function is found, you can look at the lecture notes. They are basically, but not completely, taken from Jackson's book on electrodynamics, and that's because this is, of course, the same Green's function that you use in electromagnetism. Well, it satisfies exactly the same equation, and whenever you have a problem in which the wave equation appears in 4 dimensions, you will have to work with the same Green's function, so there is no mystery here. The next step will be to substitute this Green's function here. Okay, so we have H mu nu of x will be chi divided by 4 pi d for y, and then d of x minus y. Okay, wherever we have here x, we have to write x minus y. So here we have x0 minus y0, and then minus the absolute value of x minus y vectors. And all this divided by the absolute value of x minus y, and then multiplied by t mu evaluated at y. Okay, I don't write this Rosenfeld because it should be understood that this is the one that we are using. Now this delta is different from 0, or only contributes at the point at which y0 is equal to x0 minus x minus y. Okay, this quantity is called the retarded time, TR. Okay, we are in units of c equal 1, so you don't see the c's multiplying a time anywhere. And if we decompose this integral into an integral over dy 0 and volume integral, okay, what you get is an integral over the volume, and wherever you see y0, you replace it by the retarded time. Okay, there is only y0 here in t mu. Okay. So to get t mu at the retarded time and y divided by x minus y. And this is the basic solution, the basic form of the solution. If you know t mu, you just plug it in this expression and you get automatically h bar mu. Of course, we have to evaluate this expression, and this is not simple. We are going to do it in a certain approximation which is adequate for studying waves. If we want to study waves far from where they are produced, although we are going to take into account how they are produced. This means that, well, if we assume that the region where they are produced, this t mu, is a compact region of finite size or with some characteristic size. So this t mu has compact support in that region only. And we are looking at x's which are much larger than this region. Then you can expand 1 over x minus y for small values of y. It will be small with respect to x. Okay, but this expansion makes sense. You can Taylor expand it. And okay, this expansion is a well-known expansion. Okay, so the leading term is 1 over r. The next term is xi divided by r cubed times yi, plus a half of 3 xi xj minus r squared delta ij divided by r5, and this multiplied by yj plus higher order terms of higher order, in fact, in 1 over r. Now we plug this expansion here, but I forgot to say that r is evidently the absolute value of x, and because it is just the absolute value of x and it doesn't depend on y, you can take it out of the integral, and you get an expansion in integrals of h mu bar of x. So the first term will be chi over 4 pi. You take this 1 over r outside, and then you have the volume integral of t mu evaluated at the retarded time and at y. This is the leading term, plus chi divided by 4 pi r cubed xi and yi, t mu, tr and y. And higher order terms in which you will get always products of the coordinates, first 2, then 3, and so on, and t mu. So these are these integrals of in which you the integral of the product of the distributions t mu by these coordinates are the momenta of the distribution, and they completely characterize the distribution. If, for instance, you consider a spherically symmetric distribution, then automatically all these momenta will vanish because you integrate over positive and negative values of yi, and you just get 0. So all the higher momenta would be 0, and then you would only have this first 0. You want the monopole momentum, and well, the integral of t00 will give you the mass, and you will get the momentum for the 0i components. Okay, and this is more or less what you expect. If it is static, you will not have tij's, or you will not have momentum, and basically you recover the content of the Birkhoff theorem, okay, because your h bar mu will be completely determined by t00. That's the mass density. When you integrate, you just get the mass, and you recover the formula that we got for a point particle, which we have seen. It is also the weak field expansion of the Schwarzschild metric. Okay, so this is the only possible solution, as we know. Now, for well, if we are really far away from the source, we can ignore all these higher order terms. In fact, we will do so, and we are going to consider only the first term, okay, which is a good approximation for our problem. The terms that we are interested in are the components hij, okay, because the CO0 and COI are associated to mass and momentum, and these are the ones that will be associated to radiation. Okay, so let me specialize this formula for I and j. Okay, and the thing with Tij is that we don't know, we don't have much intuition of what Tij is. However, there is a very clever trick that can be used to replace Tij by a momenta of the distribution of density of mass and energy, okay, T00. Let's see how this works. We want to compute this integral d3y dij, which is a function of y. I don't write it explicitly. Okay, I think I am using upper indices in the lecture notes, so let me put upper indices. And let me first write this as this form, which is of course completely equivalent. And then these deltas, well, they are equal to partial derivatives of the coordinates. So far I just have rewritten the original expression Tij. Now I'm going to integrate by parts, okay, with respect to this derivative. So I have decay of everything, dl dj tkl minus the integral d3y of, well, only yi stays out, and then we have decay of dl yj tkl. Now if you use Gauss theorem for this volume integral, okay, you will get over the boundary, okay, at infinity, of yi dl yj tkl, but we have assumed that t, the energy momentum tensor, has compact support, so it will vanish at infinity, and then when you evaluate this at infinity, it gives you 0. Then for the second integral, you have this derivative. When you act on this was delta, so it will give you 0, and so this derivative only acts on the energy momentum tensor. Okay, and we already have something that is clearly related to the conservation of the energy momentum tensor. We know that this Rosenfeld energy momentum tensor, we said it before, satisfies this equation, and in components this means that the 0 nu, or for the component nu equal to I or j, I don't know what is there, is L plus the ktl, for instance, this is 0, so this will be equal to minus this, and we write it explicitly. So we get minus and minus plus d3y yi dl yj, and then partial 0 t0 l. Okay. Now these coordinates are evidently independent of time. The volume element is also independent of time. We integrate them over the whole volume, so this partial derivative just can get out of the integral. And now we are going to repeat the trick using this derivative that we have here. Then we have d0, d3y. Okay, let me put everything inside of the same integral. dl of everything, dy, dj, t0l, minus, now dl yi, yj, t0l, minus yi, yj, dl, t0l. Okay, this first term is going to be transformed into a surface integral evaluated at infinity where the boundary is, and okay, under the assumptions that we have already mentioned, it will vanish. This is just delta li, so the effect is that it will become yj t0i. So let me write it directly, and this last term, using the fact that this is symmetric and that it is conserved, this is going to be minus d0 t0. Okay, let me write these two terms. First, this one, d0, d3y, yj, t0i, and then the second one is minus and minus will give me a plus d0, and then d3y, yi, yj, and d0 t0. Now observe that this d0 can again be pulled out of the integral for the same reason, and here we have the second momentum of the energy distribution. This is the quadrupole momentum. Okay, with only one coordinate, it would be the dipole momentum, and with no y's, it would be the monopole momentum. So this is already of the form that I told you that we would like to have. And how about this one? Well, we can put again this d0 inside, and using the conservation of this energy momentum tensor, this will be minus dk tki. Okay. So now this is plus d3y yj dk tki. This second term I write d3y yy yj t0. And here we do the same, we integrate by parts, Okay, we discard the total derivative because it will give us a boundary term, that blah blah blah. And the only term that survives is a term that has this minus and dkyj. Dkyj is just delta yj, delta kj, so here you have ji, which is the same as ij. But here we have this minus sign, which is crucial. We started with this, okay, and we get another term of the same kind, but with a minus. So if you take this term to the other side, what you get is that the 3y tij with a factor of 2 is equal to the second time derivative of this thing that is known as the quadrupole momentum and is denoted by qij. It's the quadrupole momentum of the energy distribution. So this is going to be 1/2, and this is the trick that will allow us to come back to the expression for h bar ij here and rewrite h bar ij equal to chi 8 pi r, and then the second derivative, well, usually this is written with 2 dots. Okay, just write it like this, okay. And this is the famous quadrupole formula that was obtained by Einstein. Okay, Einstein obtained further results that we are going to review, although in a bit sketchy form because there are too many things that can be studied for gravitational waves, and we don't have time to go through all of them. So this is the basic quadrupole formula, and now the thing that one needs is to find qij for the system that we want to study. And if we want to study if it produces waves of any kind. One first thing that we can do is to estimate what is the intensity of these waves. So since the thing that appears in the metric is chi times h, you can estimate this thing, okay, which will be given by chi squared and 8 pi r and these two derivatives of qij. Now see if the system that we are studying has a total mass m, and it also has a characteristic radius or size rc, and changes happen at a time, a characteristic time scale tc, so the characteristic speed is rc divided by tc. Now observe that qij, okay, I should have written something like this. This is just an estimate. Okay, qij scales with the mass and rc squared, so mass and distance squared. This is what you have here. Okay, so this goes like m rc squared. If you take two derivatives, okay, this will be something of this kind, and it will scale in this way. Then, taking into account this factor here, what we find is that chi hi goes more or less chi squared over 8 pi is just 2g r, which will be some typical distance, and then we have mv squared c. And the last thing that we have to do is to put back all the 2 is really not very important, to put back all the factors of c that have been omitted when we use units of c equal 1. So we can recognize this from the Schwarzschild metric, and okay, then it is easy to see that if we introduce a c squared here, this becomes dimensionless, okay, because in the Schwarzschild metric we have 1 minus 2gm divided by c squared divided by r, and this has the same dimensions as this and the metric, which are I-dimensional, okay, or sorry, dimensionless. Okay, and this has dimensions of velocity, so we just divide by v squared. Okay, just not to make this confusing, this is the characteristic velocity divided by c squared. And now we can measure this in units of, for instance, solar masses and typical distances to make an estimate of this strength. And this gives that 4.8 times 10 to the minus 20, the mass measured in solar masses, then the distance measured in megaparsecs, and Vc divided by c squared. This number is so small that, well, you see that the distances will typically be larger than a megaparsec. This is the size, megaparsec is the size of the local group of galaxies, so something has to be much larger in order for this effect to be detected. Gravitational waves are very weak because g is very weak, and also is very small, sorry, and also because this comes with a 1 over c4 here, which is also very small. Okay, so the next thing that we have to do is to try to compute this for interesting systems. So this means in this Qij. Interesting systems will be, for instance, systems of two stars that we can approximate as a set of particles, let's say two particles. Okay, well, we can start with the energy momentum tensor, okay, which in this approximation will be a sum over the masses of all these particles or stars or whatever, okay, and with delta functions. And if you just plug this expression into the definition of the quadrupole momentum, remember that this was this volume integral times yi, yj, and then t00, always evaluated at tr, okay, we have to evaluate this at the retarded time. If you plug this in, well, you get immediately Qij, so maybe I say that for this T00, this is just a sum over all the masses of the products of the positions. Okay, a very simple expression. Now we can start taking derivatives. We have to take two derivatives. Okay, and the first derivative just gives ma, and we have to be careful with the indices. Okay, so this will be x dot I xj plus xi x dot j, always a sum over a. This will be, we will call this velocity. Okay. So this is just Vj, and then the second derivative gives us, this will be acceleration, xj plus vi, vj, there are two terms like this, clearly, okay, and then there is another term with v dot j a. Now, in this approximation, everything that which is in the right-hand side has to be treated as basically special relativistic, and if the velocities are not too large, we can just approximate it with the classical Newtonian value, and Vi then is nothing but Gm, the total mass, if we are talking about the particle A, which is interacting with the rest, there is the coupling constant G, then I have to sum over all the masses which are different from that one, okay, and then the distances between XA and XB cube. Okay, so we just have to plug this in here and here, okay, and we get this expression, which is an approximate expression, but which is good enough for our purposes. So this is GMA, GMB divided by the distances cube, and then difference in positions xi A minus xi B, the same with J, and then plus a term which is just the sum over velocities, products of velocities. Okay, in the next video we are going to specialize this formula for the case of just two particles.